Now that we have the notion of what a vector valued function or simply vector function is, we're going to focus on some of the algebraic operations and concepts and properties that are associated with these functions. And in this video, we're just going to go through a series of examples and let's get started. So let R1 be this function t squared and t cubed minus 4t, and R2 be the function 1 over t e to the t and then the sine of 2t. All right, so we have two vector functions, and first let's note that these are not lines, right? The reason we know that these are not lines is simply because we have components that are non-linear. In fact, of the 6 components here, I say 6 because there are 3 components for R1 and 3 components for R2. Of the 6 components, only one is linear, and that's the x component of R1. So if we were to answer this question, it would be, well, it's really 2 questions in one. Is R1 or R2 a linear vector function, right? And it's neither, right? So neither R1 nor R2 is linear, and the reason is each of them have at least one component that's non-linear. So neither R1 nor R2 is linear, since each function has at least one component that is non-linear, right? So if we were to go through and use some kind of software, for instance, to graph these vector functions, neither of these would produce a line, right? In fact, this is a non-linear function. It's a quadratic. This is a non-linear function because it's cubic. This is a non-linear function because it is, you could say, the reciprocal function, or it's a power function where the exponent is not 1. This is an exponential function, not linear. This is a trigonometric function, not linear. So none of these are or I should say, these are the ones that I've highlighted in red are non-linear components, right? The only component that is linear is this one, right? But if at least one component of the function is non-linear, then we classify the entire function as non-linear, all right? Okay, so that is A. So let's now look at something like what is the domain of R1 and R2? Well, the domain of a function essentially is the set of all values, or values, whether it's of x or in this case t, for which the function is well defined. So basically, if we're now dealing with a vector function and we're asked to determine its domain, we're going to have to look at each component of the vector function, find the domain of each component, and then see where all 3 components are well defined, right? So essentially, it's like you're doing a domain question 3 times over. So let's start by looking at R1. So the first component and the second component and the third component of R1. These are all polynomials. So t squared and t cubed minus 4t are all polynomials. That means, right, and we know that polynomials are defined for all values of the variable, in this case t. So all components are polynomials. Therefore, R1 is well defined for all real values of t. So the domain of R1 is all real values of t. Let's take a look at R2. Right? Well, for R2 again, let's look at the now none of these are polynomials, right? So let's do them individually because they are different types of functions. So we can say 1 over t is well defined when t is not equal to 0, right? So for all values of t not equal to 0, the first component of R2 is well defined. Well, what about e to the t? E to the t is well defined for all values of t, right? The domain of your basic exponential functions are going to be all real numbers. And that's also true for your trigonometric function. So the sine of 2t is well defined, again, for all values of t. So for R2 to be well defined, all three of these requirements would have to be satisfied. So that means t cannot be equal to 0. So this implies that R2, the entire vector function, is well defined for t not equal to 0, right? So you can do that, or so alternatively, you can use the interval notation. You could say that this essentially is the domain of R2, and you can also use inequalities. So, or you could say that t has to be less than 0 or t has to be greater than 0, right? So any one of these will suffice as far as describing the domain of R2, right? So again, here's another algebraic concept, that being the domain. And if it's when you're working with these vector functions, it's like you're doing not just one of these problems, but three. So like over here, we had to remember the domain of all of these three functions, right? So then what else can we do with functions? Well, we can evaluate them. So let's say now that I know what values of t I can plug in. So for instance, for R1, if I wanted to evaluate R1 at, let's say, 1/2, right? And remember what's going to happen when I evaluate one of these vector functions, I'll get a function out. So I will plug 1/2 into my function. So it's 1/2, comma, 1/2 squared, comma, 1/2 cubed minus 4 times 1/2. So a simple substitution, right? But the difference now when compared to when you've evaluated previous functions is instead of getting a number, we're going to get a vector. So let's simplify this vector. We have 1/2. This is 1/4. And then we have, so what do we have here? This is 1/8 minus 2. So that is 1/8 minus 16/8. So that's negative 15/8. So that is our evaluation, right? And again, how to interpret this? right? We would interpret it that when t is equal to 1/2, this is the position vector that's produced by our function r1. So we would interpret it as the vector that starts at the origin and ends at this point, right? So the terminal point here is essentially that would be the point on the graph of this vector function when t is equal to 1/2, right? Let's see. So let's do another function evaluation. Let's say we take our second vector function r2, and let's evaluate that at pi over 2, right? So we can plug any number. Remember, we can plug any number that's not equal to 0, and I'm choosing to do pi over 2. So this function, we will do a reciprocal, so it's 1 over pi over 2, and then we have our exponential e to the pi over 2, and then we have our trigonometric function, the sine of 2 times pi over 2, right? Well, what does this vector evaluate to or simplify to? Well, the reciprocal of pi over 2 is 2 over pi, and then the e to the pi over 2, I'm just going to leave that in terms of e. There's nothing that can be reduced here, and there is no need for me to go to a decimal. In fact, I'd rather avoid them if possible. And then here we have the sine of pi, and then that would be 0. The sine of pi is 0. And just as a reminder, once you see you're dealing with trigonometric functions and you see quantities being given in terms of like multiples of pi, then you have to shift to working in radians, right? You might be used to working in degrees for some other reason, but here, once we see things in terms of pi, we're going to work in radians, right? So that is that's evaluation, right? But we were given two vector functions. Well, the thing is, we can actually combine them. We could figure out what is r1 of t plus r2 of t, right? This is an operation that we can do with functions where you take two separate functions, add them to get a third function, and that's exactly what we can do here. So r1 is t comma t squared comma t cubed minus 4t. And if I add to that my second function, 1 over t, e to the t, the sine of 2t, well, we know how to add two vectors, right? So presumably we should know how to add two vector functions. So we're going to add the corresponding components. So the first component of the sum is going to be t plus 1 over t, and then t squared plus e to the t, and then t cubed minus 4t plus the sine of 2t, right? And that's it. That's our sum. We can also do the difference. We can also multiply our vectors by scalars. So you can have something like this. What if we had like 2r2 of t minus 3 r1 of t. So here we would distribute, so let's set it up. So we'll have 2 times our r2 function, 1 over t, e to the t, sine of 2t, and then minus 3 times our r1 function, t squared, t cubed minus 4t. So again, order of operations, we're going to do our scalar multiplication first. That's what this is, because we're multiplying this vector by a scalar, and then we'll do the difference. And let's see if we can do all the operations together. So we will have 2 over t minus 3t, and then 2e to the t minus 3t squared, and then finally 2 sine of t, so 2 sine of, not t, 2t, right, 2 sine of 2t minus, then we have to distribute the negative 3 to both of these terms, so negative 3t cubed plus 12t, and there is our new vector function, right? let's look at part E. And part E is going to ask this question: does R2, so does R, or let's say R1, yeah, let's work with R1. Does R1 intersect the XY plane? Right? Does it intersect the XY plane? If so, at what points? My stylus is acting up, so at what points? All right. So R1, in fact, yeah. So here, let me write it. So so I'm going to write R1 in parametric form, right? So in parametric form, so let's write that down. The parametric form. Okay, this is so the parametric form of R1 is, so the x component of R1 is t, the y component is t squared, and the z component is t cubed minus 4t, right? Well, again, so this is an intersection problem. It's asking us, does this function, this vector function, intersect the xy plane? Well, in the xy plane, we know that z would have to be equal to 0. So to answer the first question, we have to ask ourselves, is it possible for the z component of our vector function R1 to be equal to 0? So is it possible for z to be equal to 0? Well, the one way to figure that out is to take our expression for z, set it equal to 0, and solve and see. Now remember, the values that we got, or the domain that we got for R1, was all real values of t. So we're going to try to find to see if there are any values of t that will make the z component equal to 0. So to solve this, let's factor out t on the left, and we're left with t squared minus 4. And in parentheses, we have a difference of 2 squares, so that's t plus 2, t minus 2. So not only do we find that it is possible, in fact, there are 3 values of t that will make the z component equal to 0. So either t is equal to 0, t is equal to -2, or t is equal to 2. So this tells me, so we can answer the question and say yes. And it's quite likely that there are 3 distinct points of intersection. I say likely because I don't know if when I plug these 3 different values of t back in to find the x, the y, and the z, are we going to get completely different points? We should, but let's see. So yes, that's answering the first question. R1 does intersect the XY plane. So then let's figure out what the points of intersection are. So let's start with t equals 0. So when t is equal to 0, x is equal to 0, y is equal to 0 squared, which is 0, and z is equal to 0 cubed minus 4 times 0, which is also equal to 0. So what this means is this vector function, right, the curve, we know it's a curve because we have, non-linear components. This vector curve actually passes through the origin, right? Let's see what happens when t is equal to -2. So when t is equal to -2, x is equal to -2, y is equal to -2 squared, which is 4, and z is equal to negative 2 cubed minus 4 times negative 2. So this is negative 8 plus 8, and that's equal to 0. So this is a different point, right? But so here's another point of intersection. Negative 2 and 4 and 0, right? And then let's see what happens when t is equal to positive 2, right? When t is equal to positive 2, x is equal to 2, and y is equal to 2 squared, which is also 4, and then z is equal to 2 cubed minus 4 times 2. So, look at what we have. So we have 8 minus 8, we have 0 again. And this makes sense, right? Why does this make sense? Because we found all the values of t that makes z equal to 0. So the fact that we got the z equals 0 here, I really didn't need to do these calculations. I could have just said, well, I know the points that we're finding are in the xy plane, so I know automatically that the z values will have to be equal to 0. This is just a confirmation of that fact, right? And there we go. So there are the 3 points of intersection of this curve in the xy plane, right? And then it could be done for the other components as well. So there we go. So we have a nice intersection problem. The last couple that I'd like to do, and I think we're up to part E, is what else can we do with functions? Well, we technically know that we can multiply functions, but since these functions are vectors, we have to think of the ways that we can multiply two vectors. So really, we could be asked to find the dot product, right? So let's find the dot product, because that's one way that we can multiply two vectors. So again, let me write down R1 just so that we have it. So we have t squared, and t cubed minus 4t dotted with 1 over t, e to the t, and then the sine of 2t, right? So even though we don't have specific numbers in the in these components, we now have functions, we can still perform our dot product. Remember what our dot product says. We're going to multiply these corresponding components. So multiply the blues, the greens, the reds, and then add them together. So we have to have t times 1 over t plus t squared times e to the t plus the quantity t cubed minus 4t times my trig function, the sine of 2t. And remember, when we compute our dot product, we no longer have components. Essentially, what we have now is a scalar, or we can call it a scalar function, because it is still dependent on t, but it no longer has components, right? So when we simplify t times 1 over t, we will get 1. And there's no real simplification that can be done for the other terms. So I'm just going to bring those down. We have our t squared e to the t. And then I'm not even going to distribute the sine of 2t. I'm just going to keep the third term here factored. So our t cubed minus 4t times the sine of 2t, right? So even, our dot product can still be computed for these vector functions. And of course, you might guess what we're going to end with, the cross product, right? So let's find the cross product of R1 and R2, right? So we're going to set up our determinant. So R1 of t crossed with R2 of t. Remember how we use our 3x3 determinant to kind of help us set up the correct products, or the correct form. So take the components of let's see. Yeah, so take the components of R1, put those components in the second row. So t squared, and t cubed minus 4t. I don't know what happened to my t here. So there we go, t. And then components of R2, they will go in the third row. So we have 1 over t, and then e to the t, and then the sine of 2t. And let's see how messy our cross product becomes. Okay, so I'll make sure I write down that intermediate step with the smaller, or the 3 2x2 determinants. So starting with our first entry here, I block out the first column and the first row, and I'm left with this 2x2. Right, so I'm left with that 2x2, and then times the unit vector I, and then minus, that's a part of our determinant formula. Block out the column with the j, so the second column, and again the first row, and we're left with t, and then t cubed minus 4t. We have our 1 over t there, and then the sine of 2t. And then finally, well, this is times j, and then plus our third 2x2 determinant. Block out the third column, and then we're left with t squared, 1 over t, e to the t, and then times k. All right. Okay, so let's do our calculation now. So we're going to have t squared times the sine of 2t. So we have that, and then minus the t cubed minus 4t, that quantity, times e to the t. So I'll put the e to the t in front, and then I'll just keep this in parentheses. And again, it's not something that we're going to expand because there's nothing that we can do to simplify. And it's important that we remember to keep the components now, right? So this is the first component of the cross product. Then let's do our minus, and then let's see what happens for the second component. So we have t times the sine of 2t, and then minus the product of 1 over t, so minus 1 over t times the quantity t cubed minus 4t, and then times j. Now this one, when I write down our final answer, right, I will actually be able to simplify this, because if I distribute the 1 over t, it will simply reduce both of these t's. But let's write down the third component now, and that's the t e to the t minus 1 over t times t squared times k. Right? And if we wanted to write our final answer using the angled brackets in somewhat simplified form, let's see what the cross product is. So I have t squared sine of 2t. If let's say we do distribute the e, right? So we'll have minus, I'll write the t cubed e to the t, and then plus 4t e to the t. So that's all the first component of the cross product. The middle component now, if I distribute the negative, then this becomes positive, so I'm going to write this term first, but also when I distribute the 1 over t, this becomes t squared, and then minus, right, because I have a negative here, and then a negative here, so those three negatives make this a minus 4, right? And then this other term here now just is minus t sine of 2t, right? So that's the middle component of my cross product. And finally, the third component, this can be simplified, not too bad. We have t e to the t, and then minus t. And there you go. So that's our cross product. So we've literally gone through as far as just the computations, and that's really what we want to get used to with these vector functions, is the fact that we can do with them pretty much all the algebra that we've done with previous functions, but now also in the context of vectors, which is why we can compute things like the dot product and the cross product. And up next, we're going to jump into calculus. Can't wait to see you then.